Hello everyone, my name is Neha and this is the 15th lecture on Introduction to Microcontrollers. In this lecture, we will learn how to read the inputs on the microcontrollers. So let's get started. We have studied so far how to write program for microprocessor output operations. In previous examples, port A bits were set as output and LEDs were connected to them to demonstrate that bits are being set by the program logic. So in the last few program examples which we have taken, in all of those we have made port A as our output, and LEDs basically show the program outcomes, like what your program is. For example, whether it was blinking LED or you're rotating the LEDs. So for all those cases, we took port A bits as your output. But now we are going to study how to write the programs for microprocessor input operations. And I would request you all to look at your curiosity board and see which register bit S1 button is connected to. So pause the video right now and see your curiosity board and figure out which is your S1 button and to which register bit it is connected to. And if you have seen already, then you will get to know that S1 is connected to RB4 register bit, and S1 is your push button, and there is another push button on the curiosity board which is S2, and that S2 push button is connected to RC5 register bit. So now you know that if you want to use S1 push button, then you have to work with this RB4 register bit. Now moving on to the next. So far we have been using port A as an output, and you know that port A is 8-bit bidirectional port, and if you put tris A is equals to 0, then port A acts as an output, and if you put tris A is equals to 1, then port A will act as an input. So I hope you remember in the initial steps of the programming, we used tris. We first selected the tris A using the bank cell, and then we used the instruction set called clear F tris A. So clear F tris A means you're giving the 8 bits 8 bit to the port A, and you are initializing it as all the register bit in port A as an output. But now if you want to make your port A as an input, then you'll have to provide 1. You can either provide all the 8 bits as 1 depending upon your program, or you can select a particular bit and then provide 1 to that, or you can set that bit high and that particular register bit will act as your input. Now here to initialize as an input, you use this register ANSL, and these register must be initialized to configure an analog channel as an digital input. So we will learn how we can use this ANSL. For now, you just understand that this ANSL register is used to configure the input mode of an input-output pin to analog, and setting the appropriate ANSL bit high will cause all digital reads on the pin to be read as 0, and it will allow analog function on the pin to operate correctly. Now let's see where do you have this ANSL. So these ANSL register, there are many ANSL register in the microcontroller. You can see one of them is here, ANSL A, and then you have ANSL B, and then you have ANSL C, ANSL T, and ANSL E, and each of them have 8-bit register. So you can see this ANSL A has these 8-bit registers starting from ANSA0 to ANSA7, and same with this ANSL B. this is the 8-bit register, and so on. If you look into the data sheet, you will see the same for N-cell C, N-cell D, and N-cell E. I have not shown it in this lecture, but you can look it up into the data sheet. And along with these registers, if you see on the left hand side, there is an address which is mentioned here. So this address defines where this N-cell A is located, and same with this N-cell B. So N-cell A is located at F38 38 hexadecimal position, and the address for N-cell B is F43 hexadecimal. Now if you see on the top, this table says special function register summary bank 0 to 31. So you see that these and then particularly if you notice here this bank 30, you will get to know that these registers basically lie in bank 30. So N-cell A, B, and then so on, N-cell C, D, and E, they all lie in bank 30. Okay, and in total we have banks starting from 0 to 31. Now next we have N-cell A. So this is port A analog select a register, and again you can see that it is a 8-bit register starting from ANSA0 to ANSA7. And all these terms that are R, W, these are all mentioned over here. What does they mean? Writable bit, readable bit, and all of these you can read on your own. So I'm going to read this. Analog select between analog or digital function or pins RA, and then starting from 0 to 7 respectively. So if you put 1, it will work as analog input, okay, into these bits. So pin is assigned as analog input, digital input buffer disable, and if you provide 0, then it will act as digital input output, and then pin is assigned to port or digital special function. So if you provide 0, then it will act as digital input output, okay, and when you provide 1, then this will act as your analog input. So when setting a pin to an analog input, the corresponding trace bit must be set to input mode in order to allow external control to the voltage on the pin. So in that case, you have to make trace is equals to 1 if you want to make it as an input mode. Now next is this analog control. Again, I'm trying to get in deep with N-cell register, and you can see here this particular content I've taken from the data sheet. You can refer to this 12.2.6 which talks about analog control. So I'm going to quickly read here. It says N-cell register is used to configure the input mode of an input-output pin to analog, and setting the appropriate N-cell A bit high will cause all the digital reads on the pin to be read as 0, and it allows analog function on the pin to operate correctly. So the state of the analog N-cell A bits has no effect on digital output function. A pin with its trace bit clear and its N-cell bit set with still operate as a digital output. Okay, so this is the same thing. If you make your trace bit as clear, which means 0, then its N-cell bit set will still operate as a digital output, but the input mode will be analog. So the input mode is going to be analog in that case, and this can cause unexpected behavior when executing read, modify, write instruction on the affected port. So this whole line which says a pin with its trace bit clear and its N-cell bit set will still operate as a digital output, but the input mode will be analog. So we are going to actually do this thing. In our coming program for this lecture, we will be setting up the trace bit as clear, and we'll be using N-cell, and we are providing the input. Our input mode in that case is going to be analog. So that's it, and you can quickly read here to the note. The ANSL bits default to the analog mode after reset. To use any pins as digital general purpose or peripheral inputs, the corresponding ANSL bits must be initialized to 0 by user software. Now I'm going to show you a quick example, and this has been taken from the data sheet. So that's how you initialize the port. The whole example is given here. So you can also refer this example from your data sheet. Go to the example 12-2, which says initializing port A. And this code example illustrates initializing the port A register. The other ports are initialized in the same manner. So when it says other ports, which means you can use port B, port C, or port D, etc. So these are the basic instruction. Bank cell select port A, clear F port A, and then bank cell LATA, clear F LATA. We haven't used this latch A, but whatever you read or write on the port A or port B, the same thing immediately saves on these latch register, latch A or latch B or latch C, and so on. Bank cell ANSL A and clear F ANSL B, digital input output mode. Bank cell trace A, move the literal number, this literal number to the trace A. So if you move this literal number to the trace A, then what is going to happen? You'll read here, you'll get to know. Set RA starting from 3 to 4. So if you see here, this is 0, 1, 2, 3, 4, 5. So 3, 4, 5 bits are basically set as high, and rest of the bits are set as 0. So if your 3 bits are high, starting from 3 to 5, then they will be considered as your input. You know that when you give trace as 1, trace to the 1, then it will be considered as your input, and if you give trace to as 0, then it will be considered as output. And that's what you see here, RA from 0 to 2 as your output, and then you have these two also as your output, which is your RA6 and RA7. And only these 3 pins, register pin, which is RA3, 4 and RA5, has been made as your inputs. So similar to this, we will be using in our button input program, and you will see that in the next coming slides. So moving on to the next slide. So now I'm going to show you the program which is based on button input, and I'll show you how the whole code looks like and how the flow chart for that program looks like. But the first thing which I'll show you is the goal, what we are trying to achieve, so that you'll have like a big picture what we are trying to learn later on in this lecture. So I have put up a small video which already has a code. So this development board already has a button input code, and it will tell you what is happening, and that's what we are going to learn in the coming forward in this lecture. So I'm going to play this video. So you can see that I press this switch S1, and then when I press the switch, then the LED is off, and when I release the button, then the LED is turned on. So remember, when the button is pressed, then the LED is off. When the button is released, then the LED is on. Okay, so this is a very simple program which I have made, and I'm going to show you the steps which I have used. And so let's see the next slide. Okay, so this slide talks about the flow chart for this particular program, and you already saw that when I was pressing the button, at that time LED was off, and when I release the button, S1 button, then the LED was turned on. So I have to like create a code in that way, in that way in which it can work. When I press the switch, LED is off, and when I release it, LED is on. Okay, so this is a flow chart, and it says read button. So read the button, and then it's a decision box. It's going to check whether RB4. So you remember I asked you to check which S1 push button is connected to. So S1 is connected to RB4. That's why I've put up here. So whether RB4 is equals to 1. When it is 1, it means the button is released. So what does it mean? So RB4 is equals to 1 means your LED is on. Okay. And when I release the button, then the LED is going to be turned on, and that's what it says here. So when the button is released, then RB4 should be equals to 1, which means LED should be turned on. Okay, so this decision box is asking this question, whether RB4 is equals to 1 or not, or whether button is equals to release. So these two statements are the same thing. Okay, so if it is released, okay, which means LED is on. So yes, the button is released, which means LED is turned on, means button is released. Okay, and then it will go to again to this loops. I've created this loop, and then again it will check if the button is released or not, if RB4 is equals to 1. So let's say if RB4 is equals to 0, which means it is off or button is pressed, then you will say that this condition is no. Okay, so no means here, that means the LED is off, means button is pressed, and go to again this loop. So you understand this is such a small and simple flowchart for button input. And now I'm going to show you. So this is the same flow chart. It just tells you what will happen when the button is released, and there will be another block diagram or the flow chart which is coming after this slide, and that will tell you what will happen when the button is pressed. So this one is for the release. So when you release the button, you know that the LED will be turned on, and that's what it is showing. So read the button, it is pressed, and then the green thing which you see here is basically working in this one. So read the button again, and then I've added these two extra instruction because sometimes students get confused. So I've added these few more blocks to get an understanding of this program. So read the button, RB4 is equals to 1, button is equals to release, yes or no. If it is yes, button, read the button, and if RB4 is equals to 0, button is equals to pressed, yes or no. If it is no, then LED is on. So this is the extensive version of the flowchart which you saw previously. A few blocks have been added, and this particular flowchart, especially the green blocks, it tells you what will happen when the button is released. So if your button is released, so this is the cycle it's going to follow. Okay, and when the button is pressed, then this is the cycle it's going to follow. So you see, this is the cycle it's going to follow. So you can read it quickly. Read the button, RB4 is equals to 1 or not, button is pressed or released. So let's say if it is not, then no, then LED will be off, and then again it is going to read the button, is the LED is equals to 0 or button is equals to pressed or not. If it is yes, then again it will go to this read button input. Okay, so you see when the button is pressed, then this cycle is going to be this cycle will be followed. All right, now next we are going to see the different instruction set we'll be using for button input program. So we will be using bit test F, skip F set, this instruction set, and I have discussed this instruction set couple of times in the previous lectures. This is the syntax for this instruction set, where F is your file register, B is your bit, at whichever bit you want to work on. All right, and this is BCF, which is bit clear F, and this is the syntax for that. F is again the file register. B will tell you which bit you want to basically clear. So bit B in register F is cleared. So if you assign a particular bit, then that bit will be clear. And then BSF, it works opposite to what the BCF works. It basically sets the bit. So whichever bit you assign here, it's going to set that bit to 1. So these three major instruction set we'll be using in this program. Now let's quickly jump to the programming. So you'll start the program by selecting the bank cell and cell B we are using, because if you see the input through which we want to provide is our push button S1, and S1 is connected to RB4, and B is it's basically your port B. So we have to use Ancel B, and Ancel B, you know, that's used for defining the input mode, and that's why we have used here Ancel B. So bank select Ancel B. Ancel B register is used to configure the input mode of an input output pin to analog. Okay, and then you will make a clear F Ancel B port B. Inputs mode is not analog, that is digital. If you provide this clear F, so the port B input mode is going to be digital input mode. And then you will select bank cell port A. This step we have been doing in the past also. Port B, Tris A and Tris B are in the same bank. So you can we are using port A because you can use port B, but then we are using port A here because we are using the LED which is already there in our development board. We are not using external LED. You can use that. If you do that, then you have to use maybe another port, or you can even utilize this and add up new LED. Bank cell port A, and then clear F port A, initialize the port A, clear F port B. So port B lies in the same bank. You can write in this way. You don't have to select it multiple times. So clear F port B, and then clear F Tris A. So which means making all the bits of port A as output. And then next is moving this literal number, which is 0001 and 0000 to the working register, and from working register moving it to the Tris B. So if you move this to the Tris B, it means you're setting this particular bit which is here as your input. So if you count from here, this is your RB0 to RB7. So this place is your RB4, and that's what it says here, set RB4 as your input. Okay, so you follow these steps, and then next thing, so this is just like initializing initializing the input. And so this says Ancel B, if you give all zeros means digital input, and if you give all ones, then it means analog input. So right now here Ancel B is clear F, which means you are making it as a digital input mode. And then next we have is the loop. So this is the main loop which will basically test for fourth bit, which is RB4. So starting with this bit test F, skip if set. Okay, so this is your port B, and this comma 4 indicates your bit number. So fourth bit number is this test RB4. So RB4 is at your fourth place in working fourth place in port B. So it's going to do the bit test, and it's going to skip if it is already set, which means it is 1. So it's going to skip if it is set. So let's say if it is set, then it will skip this step and then it will directly jump to this one. So right now I'm skipping this step and directly jumping on to this. I'm taking one condition when it is set. So it will go to this condition and then it will check again bit test F, skip if clear. So if it is clear, then it's going to skip. If it is not clear, so I'm assuming that it is not clear, so this is not going to skip this step. It will go to this step and it will tell that bit set F, port A is equal port A comma 4. Bit set F means, and then please notice here that you have port A here and port A here for BCF and BSF, and bit test you are using for port B. So at port B, which is connected to your switch S1, you're testing it. You're doing the bit test for your switch, which is S1, and you're clearing or setting the bit on your port A, which is your RA4, and RA4 is connected to the LED. Okay, so you're doing BCF and BSF for your LED, which is RA4, and BTF, SC, and BTF as you're doing it for your port B, RB4, which is connected to your switch S1. So again, so it's if it is not clear, if your switch S1 is not clear, which means it is 1, then what is going to happen? This instruction will be executed, bit set F. So set RA4 if set RA4 is equals to 1 if RB4 was high. Okay, so this step you I hope you understood. And then let's see if you are doing the bit test and it is not set. So if bit test F skip if set is not set, it is 0, then it will not skip this step and it will go to this step and it's going to make your LED as low, or LED as clear or is equals to 0, which means your LED will be off. Now if you have any confusion here, then remember this thing. When button S1 not pressed, which means it is the release, then at that time the condition is 1. Okay, because you remember in the initially we have already given the input as RB4 as your 1. We have already said that, so that is the set condition is equals to 1. When the button is not pressed, it is released, already a set condition, which means in that case your LED should be turned on. And then second case is that when the button S1 is pressed, not released, which is a reset condition, which means it equals to 0, then this your LED should be off. It should not be on, it should be off. So I'll just quickly make the correction here. So this should be off, or just write it here, LED off. Right, so in that case your LED will be off. So you see here, remember these two things, because sometimes students get confused. They think that when you press the button, then only your LED will be turned on. But the program which I made basically do the opposite thing. When you release the button, then your LED will be on, and when you press the button, your LED will be off. Okay, so make sure you remember this thing, and if you have any confusion here, try to relate this code with what is happening here. These two steps you see here, try to relate with this, and then it will be easy to understand. And then so once you all these so this loop is once you perform this, then it will go to loop. So loop is your label here, loop is your label, so it will go to this loop, and then the program will be and this loop is going to go, it will go forever. So this is a very small program for button input. Now next, we are going to see the button input program on MPLAB. So this is the same program which you have seen on the slides. So I have made my button input as project, and under that source file, if you click there, you can create an assembly file, and under that I have put up this code. This is the configuration, and then this is my simple code over here, main program code, bank cell, N cell B, clear F, N cell B, port B, digital bank cell port A, and this is the same port B, trace A and trace B are in the same bank. Clear F port A, initializing the port A. Clear F port B, initialize the port B. Clear F trace A, set all bits in port A as output. Moving this literal number to the working register, and then working register to the trace B, setting RB4 as input. So you have already given this input. You have set the input RB4 as equals to 1. Okay. So as I told you that my program is opposite. When you release the button, then your LED will be turned on. So you can make it opposite way. When you press on the button, then LED will be turned on by giving by changing things over here. So I'll leave that a question to you, like what change you are going to do here, which will make your LED turn on when you press the button. Okay, and then this is the loop program, bit test F, skip if set. So and then port B, comma 4. 4 is your for fourth bit, which is in your port B, which is RB4 we are talking about, and then BCF port A, comma 4, and port A, you know that RA4 we are working on. So instead of this 4th bit, you can set it to something else. Maybe you know that there are 4 LEDs on our development board, starting from RA4 to RA7. So you can pick any one of them. And if you don't want, you can attach external LED and have this program run on that external LED. Okay, so we have used the same we have used the RA4 LED, and we are going to see demonstrate this button test on that LED. And then you have bit test F, skip if clear, board B, comma 4, and then BSF, set the bit port A, comma 4, LED will be on, and then loop will be go on forever. So it's the same program. Just wanted to show you here, and you will just click on this clean and build, and then if you have written the code correctly, then it should show you something like this. Okay, build successful. So I would request you to just at least try the same code which I have put up here on your MPLAB, and see if you are getting the same results or not. And then you can do manipulation over here and try to play with the code, and you will learn a lot, and you will get to know that how easy this programming is, and how you can use different instruction set to create new code. Okay, so we have our build is successful. Now what I'm going to do next is I'm going to connect, use the MPLAB IPE and connect to the board. So I have my board with me, and when you connect, then it will show you that it is connecting to starter kit. So it is already connected. So meanwhile, so now I'm going to find the hex file. So you click on the hex file, and then I already have this hex file here, but I'll quickly show you how I went there. So this was my button input, and then I went to this dist, and then default, production, and then hex file. So I selected my hex file, and the next step is to program. So if I click on the program, then it's going to put up the code into my development board. And you already saw the code in the initial slide that when I press the button, the LED was off. When I release it, LED was on. So you already know what was the result. So now let's move on to the next. So we already saw how the button input program worked on MPLAB. Now, next we have how you're going to rotate LED on each button press. So far, we made the code, uh, and it was rotating the LED by itself. Now, I want you to make a code on where when you press the switch, then it is going to rotate the LED. Okay, and you should rotate the LED towards right instead of left, and see how the code works out. So this is an assignment for you. That's all for this lecture. Thank you so much for watching.